What if I told you that you could build your own DEX, just like Uniswap, from scratch in under 200 lines of Solidity code? And by the way, not just a toy version, but a production-ready AMM with real liquidity pools, token swaps, and fee collection. Well, that's exactly what we are going to do in this series. I'm Hossein, and here's Codechunk. Today, we are starting an epic journey into DeFi development. We're going to be building a complete automated market maker from the ground up. And by the end of this series, you'll understand exactly how protocols like Uniswap, SushiSwap, and PancakeSwap work under the hood. So if you are ready to level up your blockchain development skills, make sure to hit that subscribe button and let's dive right in. Before we start coding, let's understand what we're building. DeFi, or decentralized finance, is essentially rebuilding the entire financial system on the blockchain. So instead of banks, we can have smart contracts, and instead of centralized exchanges like, for example, Coinbase or Binance, we can have automated market makers. So let's just think about traditional exchanges like Coinbase, for example. They have order books and market makers and a centralized authority controlling everything. But what if we could create an exchange that runs itself? No CEO, no servers, no single point of failure, just pure code on the blockchain. That is exactly where automated market makers, or AMMs, come into place. So what exactly is an AMM? An automated market maker, or AMM, is a smart contract that acts as a decentralized exchange. But instead of matching buyers and sellers like traditional exchanges, it uses mathematical formulas to determine prices and execute trade. Here's how it works. Imagine we have a pool containing two tokens, like exactly this AMM liquidity pool. Let's say ETH and USDC, for example. This pool is like a virtual vault that holds both tokens, right? So when someone wants to trade ETH for USDC, they don't need to find another person willing to make the opposite trade. Instead, they trade directly with the pool. The user deposits ETH into the pool and receives USDC back. So the smart contract automatically calculates how much USDC they should receive based on the current ratio of tokens in the pool. Where do these tokens come from? They come from liquidity providers, people who deposit both ETH and USDC into the pool. In return, they receive LP tokens, or liquidity pool tokens, that represent their share of the pool, and they earn fees from every single trade that is being done on the DEX. It's like owning a piece of decentralized exchange that operates 24/7 and generates revenue from trading fees, right? That's pretty cool, right? Now here's the magic behind AMMs, right? The constant product formula. And now that we have a little bit information about DeFi and AMMs, it's time to understand this formula. This formula looks pretty simple. X multiply Y equals K, right? But this little formula is what makes the entire system work, believe it or not. Now, this K, which is our constant, must stay constant, okay? Across the whole platform. Let's understand this with an example. Let's pull up our calculator. Let's say our pool has 100 ETH and 200,000 USDC, right? So the K would be 20 million. Now, let's say there's a user who wants to trade 10 ETH for USDC, right? So they add 10 ETH to the pool. So now we have 110 Ethereum in our pool. If we now multiply this by our 200,000 USDCs, now the constant is 22 million, which is not constant actually. 2 million got added to our constant variable, right? So it's false. So we need to give some USDC to the user who's depositing 10 Ethereum to our pool, right? So how much? How can we figure that out? Well, it's basic mathematics. So now we have X as 110 multiply Y equals 2 million, right? So how can we actually figure out what number should our Y represent here? So we just need to say 20 million which is our constant, divided by 110, which is this number. So we can basically say this. All right. So we need to keep this much of USDC in our pool, so our K stay 20 million, right? So now that we have 200,000 USDC, so let's say 200,000 USDC minus this, we need to get rid of this much of USDC in our pool. So we need to give this much of USDC to the user depositing Ethereum to our pool, right? So the K stays constant. So as a recap, the pool started with 200,000 USDC and now it has this much, right? So it means that the user who's depositing Ethereum to our pool got this much, this number of USDC received. Now, before we start writing any code, let's understand what we're building, like what structure should our project maintain in the whole process, right? So our AMM will consist of two main contracts. The first one is gonna be the AMMPair contract. This is the heart of our AMM, which handles adding and removing liquidity, like so. It handles token swaps in both directions. And by the way, I separated these two functions for two directions to understand better, because it's going to be a little bit tricky and hard to understand, I think, for the first time for someone who just started writing smart contracts. It actually handles fee collection and distribution, which is really cool. And our functions will use CEI pattern, which is a security best practice in developing smart contracts using Solidity, and also reentrancy attacks. Now the second one is going to be the AMMLP contract, right? This is our Liquidity Provider token. It's a standard ERC20 ownable contract or token that represents the ownership shares in our liquidity pool. You'll understand this in a minute. When someone adds liquidity, they get some LP tokens. And when they remove liquidity, they burn LP tokens. Now here's how these two contracts work together. So for example, let's say user adds liquidity and the AMMPair contract mints LP tokens and user will receive LP tokens, right? Next up, user swaps tokens, right? So AMMPair contract calculates output using constant product formula, and then it executes the swap, right, in both directions. Next up, we have removing liquidity. So let's say user removes liquidity. AMMPair contract burns LP tokens, right? It burns LP tokens. User will receive their own tokens. This is how these two contracts work together. And if you don't understand anything about this at the moment, it's going to be complicated. You'll understand as soon as we start developing this functionality all together. So don't worry about it at all. All right, enough theory. Let's start building. We'll be using Foundry, which is hands down the best framework for Solidity development. If you don't have it installed yet, pause the video, go find out how to install it using getfoundry.sh, which is their official documentation of Foundry, and install it. So I'm going to assume that you have it installed at the moment. So let's create our project, right? So I'm going to say forge init, and I am going to wait for this to get initialized. And as you can see here, we have our necessary files here. So let's go ahead and delete the sample ones. We'll be using these folders later. Don't worry about it. Perfect. Now we have everything we need to start building. Now it's time to create our first contract. This contract is going to be SwapCraft LP.sol. You can name it whatever you want. Okay. LP stands for Liquidity Provider. You can include it in the file name if you want. Now, in here, I'm gonna start with defining the license. I'm gonna define my Solidity version, and now it's time to define our contract, SwapCraft LP. Actually, let's zoom in a little bit so you can see better. Now, the SwapCraft LP is our Liquidity Provider token contract. We're gonna build a standard ERC20 token with a special twist. Only the SwapCraftPair contract can mint and burn these tokens, this Liquidity Provider token. That's another contract. That's the second contract we're gonna be building, so don't worry about it for now, and let's just focus on building this LP or Liquidity Provider token, right? So first of all, I'm gonna say this contract is gonna be ERC20 and ownable. Oops. Ownable, right? So these two keywords are coming from OpenZeppelin, which is a package that we're going to be installing at the moment. So if you go to this address, you can have access to all their contracts, which are standard and perfect. You can install using this command here. So let's go ahead and copy paste it. So in here, I'm gonna wait for it to get installed on my project. Once it's installed, we can go ahead and import these two keywords, these two files actually, ERC20 and ownable, from these contracts. I'm going to say import ERC20 from lib/OpenZeppelin contracts/contracts/token/ERC20/ERC20.sol. And next we have ownable from the same path, ownable from lib/OpenZeppelin. Oh, thank you, my AI agent. So now that we have access to this ERC20 and ownable keywords, actually files, and we are inheriting from them inside our Liquidity Provider token, we need to verify that we are using them inside our constructor. Okay, so in here I'm going to define my constructor, and in there I'm gonna exactly use constructors of ERC20 and ownable. So let's go ahead and take a look here in constructor. So as you can see here, ERC20's constructor gonna receive a name and receive a symbol, right? So for ERC20, name of the token would be SwapCraft LP, and for the symbol I'm gonna use SCLP. And then for ownable, let's go ahead and take a look at ownable. Let's search for constructor. Okay, the constructor receives an initial owner, which in our case we're gonna use message.sender, because later on we're deploying this contract using our next contract that we will be building. So message.sender would be the contract that owns the SwapCraft LP token, which is going to be SwapCraftPair contract. Perfect. Now that we have access to ERC20, ownable, and our constructor, and we initialize these two contracts using our constructor, it's time to create some functions, right? So the first function is going to be something called mint. So let's go ahead and create mint function. Mint function is going to receive a to address and a U256 amount. So basically we're going to be minting this amount of our LP token to this address, right? It's going to be an external function. By the way, we have access to this only owner modifier using this ownable. So because this SwapCraft LP token, our great contract, is going to inherit from ownable file, which we have here, we will have access to this only owner modifier. So we can actually see it right here. As you can see here, there's a modifier called only owner. And if we go ahead and see the function that this modifier is calling, we can see that it says if owner is not message sender, revert it with a custom error. we will be talking about these custom errors a lot, and this is going to be a pro course, so we're definitely gonna import and use a bunch of these custom errors later on in the course. Now inside here, we are gonna just simply use underscore mint. And what is this underscore mint? Now, if you take a look at ERC20 contract and search for underscore mint, we can basically see that there is this function available. Actually, we can use it because we are importing ERC20 and we are inheriting from it inside our SwapCraft Liquidity Provider token. So we don't need to create any logic in here. We are just gonna be using this mint underscore mint function, which is coming from ERC20.sol. Perfect. Now, just one more function that we need is gonna be burn. So we have address from in here, and UN256 amount is gonna be an external function, and it is again gonna be calling underscore burn function, again coming from ERC20 contract, right? So now if we search for burn, we can see that we have that implemented, and we can just simply gonna go ahead and use it, right? Now let's talk about a little bit about these two functions, huh? This function actually mints new LP tokens to a specified address, right? So to address is going to be the address we are minting to, and the amount is going to be the amount of tokens we are minting to this to address. Okay, this can be only called by owner, which by the way is going to be the address that deployed our contract, which again is going to be our next contract that we'll be implementing, the pair contract. So when are we calling this function? Where are we using this function? In a short explanation, I'm going to tell you now, and we'll be building it later. We are calling this function when users add liquidity to our pool. Think about it. User is going to provide some tokens to us, and actually to our pool, and we are giving them some SwapCraft Liquidity Provider tokens, right? And for burn function, we basically have those rules, which I didn't apply, so only owner. This function burns LP tokens from a specific address, right? This amount of LP tokens from this address. Now, burn function is going to be called when users remove their liquidity from our pool, right? So they once gave us some tokens. We gave them SwapCraft LP token. Now they're gonna get back their tokens. So we are going to burn their previously received LP tokens. Make sense? Perfect. But before going further, think about it. There might be a problem in here. There actually is a problem in here, which I am suggesting you to pause the video and think about it. What is the problem in here? What can we do? What is that bug we will be facing if we don't fix it right now? Okay, I hope you found the issue. The issue is that if we go to this mint function, or even this burn function, these general functions are controlling if the account is address 0. So what is this account? To account and from account, right? We have this in burn as well. So let's see. We have this in burn. This account is being controlled. So if we pass a 0 account to these functions, they are going to throw an error, and that's fine. That's handled right away. But we don't want anyone to send an amount of 0 to our functions, right? We need to handle that ourselves. And this is going to be perfectly done using a custom error and a modifier. How? Let's go ahead and implement our modifier. So I'm going to say modifier valid amount. It's going to take a UN256 amount, and I'm going to say if amount is equal to 0, then revert it with a custom error. This error, I'm going to name it SwapCraft LP -- invalid amount, or we could say must be greater than 0. Okay, great. And then I'm going to use underscore after this block, which means first go ahead and do this and then continue with running the other parts of the function. Great. Now, how can we actually use this? First, let's go ahead and implement this error. Perfect. Now in here, after only owner, we can go ahead and pass that amount to our modifier. Great. And also in here. Perfect. It's time to go ahead and create our next contract. Now we are ready to build the heart of our automated market maker, the pair contract. This is actually where the magic happens, where users can swap tokens, can add liquidity, and earn fees, right? So before we dive into code, let me explain what this contract does and what we are going to be building. This contract manages a trading pair between two ERC20 tokens, right? So users can add liquidity and receive LP tokens in return. Users can swap one token for another using the constant product formula. Our contract is going to be collecting a 0.3% fee on every swap, and it follows the checks, effects, interactions pattern for security in smart contract development. Let's go ahead and start building. Inside SRC, I'm going to create a file called SwapCraftPair.sol. We're going to have SPDX. We're going to define our identifier, pragma solidity, same version. And in here, I'm going to say SwapCraftPair, which is our contract. Now, before doing anything, what we are going to do, we're going to be building our constructor, right? Now, what is this constructor supposed to do? The constructor takes 3 parameters: the LP token contract and 2 ERC20 tokens for our pair, right? So first of all, in here, I'm going to say SwapCraft LP token. So our liquidity provider token is going to be of type SwapCraft LP, which we're going to import. Then I'm going to say IERC20 token A and IERC20 token B. Let's go ahead and import these things. So I'm going to say import SwapCraft LP, which is the contract we've been building. And we're going to say import IERC20. Thank you, my AI agent. And these 2 tokens, token A and token B, are going to be of type this IERC20. So let's take a look at this. This is not a contract, actually. This is an interface which has some events, as you can see, some functions. This is just an interface for working with ERC20 tokens. So by using this interface, we have access to some functions like total supply, balance of, which takes an account, which takes an actually address of account and returns a uint256, which is the balance of that account. We have transfer, allowance, approve, and transfer from. And don't worry if you don't know anything about this stuff. Now let's go ahead and initialize our storage variables here. So we're gonna have SwapCraft LP public immutable ILP token. So the reason I'm setting this to immutable is because we are setting this once in our contract. It's not going to be changed or modified by any chance, and we are just setting this for the first time when we are initializing our pair contract or deploying our pair contract using this constructor, right? After that, I am going to say IERC20, again public immutable, I token A, and this I stands for immutable. And finally, we have the same thing for token B, right? Great. Now inside our constructor, we're setting these things. So I LP token is going to be this incoming LP token. Token A is going to be this incoming token A, and we have same thing for token B, right? But before setting this stuff, we need to do some checks, right? What if these addresses are zero address? What if token A equals token B? We want two different IERC20 tokens, right? So let's go ahead and do that checks before actually setting these addresses to our storage variables, right? So the first check is going to be if address of LP token is going to be address 0, then go ahead and revert with a custom error. So we're going to say SwapCraftPair invalid LP token. Then if address of token A or is actually address 0 or address of token B also equals address 0, so one of them, then go ahead and revert with this error. You can see how powerful my AI agent is. It knows exactly what I'm doing here. Invalid per token. And finally, if address of token A equals address of token B, then go ahead and revert with another custom error. SwapCraftPair must be different addresses. Or, yeah, you're right, my AI, different tokens. Great. Now we need to implement these custom errors. So before my storage variables, I'm going to say error. I'm going to make a copy out of it. Let's go ahead and duplicate this a few times. This is my next error, and this is my next error. Perfect. Now that we have our contract and our constructor ready, it's time to build some functions, right? So what functions do we need in our contract? Probably we first need to define a function called add liquidity. So let's create something like an interface first, and then we'll be building out on this. Next one is gonna be remove liquidity. The next thing can be swap function actually. So let's make two swap functions so you better understand what's going on in a project like a DEX, for example. So function swap A for B and function swap B for A. We probably need a function for getting reserves of our two per tokens. We need a function for, let's say, calculate swap output. And I think for now, these are going to be enough. So we are going to be building on these functions in order, right? And there we have it. We have successfully built the foundation of our SwapCraft AMM with a complete per contract structure. We have got our LP token integration, proper validation in the constructor, and all the essential function signatures that every AMM needs, from adding and removing liquidity token swaps and reserve calculations. Right now, these functions are empty shells, as you can see. But that's exactly where we want to be at this stage. In the next videos of this series, we're going to bring this AMM to life by implementing all of these core functions with the proper constant product formula, fee calculations, and of course, we'll be writing comprehensive tests to make sure our AMM works flawlessly and handles all the edge cases. Testing is crucial when dealing with DeFi protocols since we're handling real money. If you found this helpful, smash that like button and subscribe for the next part where we'll be completing the implementation and make our SwapCraft AMM fully functional. So, thanks for watching and see you in the next one.